Is the day you've been waiting for, path integral control. So first I want to talk a bit about the motivation and why we can't just solve the HJB equation in most cases, and what we gain by moving to the path integral formalism. So the HJB equation, you can view these little dots on the grid as being states oriented in time, and we have some initial state t, x of t, and some final time point, and the states here correspond to the terminal condition where we have j evaluated. Right, so we have knowledge initially, j, x of t at the beginning of our algorithm, and we want to move the information backward in time to the state we're interested in, the state where we're acting on the control. And you can see that to do this, we actually need to define j in the set of all possible, evaluate j sequentially, first here and then here, in the space of all possible states, this reachable set from x of t. And it doesn't matter how rare a particular state is, to make j perfectly defined, we need to evaluate all possible states we could reach starting from x sub t. And that's in this discrete case, where there's just basically an integer number of states, right? So this is state 1, 2, 3. It's doable, but as the dimension increases, it becomes a lot harder, right? Because this is a kind of volume in space, and so the number of evaluations of j is order j is order tau minus t raised to the dimensionality of your space, roughly in this kind of simple place where there's where your transitions are sparse. Now your transitions might not be sparse; they might just be approximately sparse. For instance, if there's kind of a rare chance for you to jump to a distant state, then of course the volume will grow bigger, faster. You'll have to cover basically all possible states. But if the transitions are kind of sparse and you're kind of confined to small jumps in state space, this is kind of roughly how the number of calculations scale. And the dangerous thing about evaluating the HJB equation like this is, any failure to evaluate j kind of creates this sort of backward propagating cone of undefined values. So if we haven't evaluated j here, then that means we can't evaluate j here, and so there's kind of this increasing volume of excluded space where we can't evaluate j. We'd have to go back and fix our lack of knowledge here before we could increase the space at which we know how to control our system. So overall, HJB is delicate in the sense of this sort of propagation of NAs, of undefined values, and inflexible. Right? If we're initially interested in this state, and then all of a sudden we realize, oh, actually, we're interested in this other state here, then we'd have to kind of redo the entire HJB recursion. A lot of the work is done, but there's still this kind of problem in terms of figuring out which work needs to be done, and it becomes complicated. So it's delicate, it's inflexible, and it scales badly with dimension. And also, with continuous moving to continuous time, right? So this part here, the number of time steps in continuous time, this goes to infinity. Okay, I mean, they're not complete deal breakers in this discretized space where the dimensionality is small. In fact, for the coin toss problem, we actually can solve the HJB equation exactly. And that actually makes it a really good reference problem because we can use the solution for the HJB equation to check and see if our increasingly complicated path integral algorithms converge. So in contrast, the path integral algorithm is a Monte Carlo estimate. So that means that basically we're going to be calculating things like this exponential of the minus cost to go at a particular time as expectations over paths. That start at your initial point of this some kind of exponential weight over the path. Right, so this can be evaluated in a Monte Carlo form as just a kind of 1 over some set of paths sampled from the reference measure, which I'll call K, of this cost function. Whoops, here. I'll write this as a sum of the time points. Right, and so the variance of this scales like, so the variance of this is an expectation of this z, right? So the variance of this estimator for z is, it scales like some initial variance over the number of samples we take, if everything is going well and we kind of converge to the normal approximation. And that means that if we wish to calculate z within a certain accuracy, this means we can get z hat in order n calculations. So scales well with dimension, right? This is the magic of the Monte Carlo method, that we can calculate high dimensional integrals without kind of paying this cursive dimensionality price. And the other thing to keep in mind, this related idea, is that really we only need to consider paths in proportion to their probability. So we gain this kind of speed up by sort of ignoring extremely rare states. They don't really contribute much to our expectation. And that's a really crucial element of this procedure. Right, so the idea is, okay, so in the continuous case, I'll just write this in purple because this is not what we're sort of interested in. You have this Feynman-Cash lemma. I don't know how do you write? I think it's like just Feynman-Cash, I think it's pronounced, but it's like Hungarian or something. So, and this provides a link. There's a link between the partial differential equation on one side and the path integral sum over paths on the other. And so this is, in our case, the Hamilton-Jacobi-Bellman equation. Right, and so this is actually a little bit tricky to prove properly because, there's sort of this question, do you have the right path measure in the continuous case? So it's a little tricky to show all your Jacobians work out. And that, there's issues with the Ito versus Stratanovich discretization schemes. But in the end, you kind of get what you expect. expect based on the discrete case. So if you didn't know about all these kind of tricky stuff that can come up, you would still probably end up calculating the right thing. But yeah, so in the discrete case, it's much easier. So in the discrete case, we can just kind of, you can just read off the result. You don't need to be super clever, right? So once you have the recurrence, the linear recurrence relation. So once your HJB has been cast as a transfer matrix equation, that just means it's a linear recurrence in time. So yeah, so just to recall the result from Todorov, or from our forcing of the result into the Todorov form, right? In general, you have this case where we have e to the negative j x of t over temperature. This is z of x of t. And this is equal to the sum of xt plus 1 times e to the vx of t, some times z x of t plus 1. Right, and we can just move back another step in time, or move forward another step in time, I guess, depending on moving backward, forward in time. Right, so we've expanded this guy all the way to the terminal condition. Okay, so that's our z of x of t. And you can see we have these sums over each possible state at each possible time. So we can kind of recast this as a single sum over all possible strings of states, or paths, which we'll write x of t to tau. So note that this actually is, so just to be clear about what this is all states that start at x of t, and every possible xt plus 1, xt plus 2, etc. So the sum of our paths is taken, and then collecting these k's, we see that we have this product of k x t prime given x of t prime minus 1, whereas t prime is, I'll make this a plus 1 and a, oops, t equals t to tau minus 1. And then just collecting all the exponential terms, we have that this is multiplied by e to the negative 1 over t with the integral. Well, I'll write it as a sum, it's discrete. Okay, so that's not too much work to see that this is just because of the Markov nature of our paths, this thing is just the probability of a particular path, right? So this is equal to the sum of all paths, probability of the path according to that propagator k. And then this I'll just write as the total potential experienced by the path. Right, so that's the path integral algorithm in discrete form. There's really not a whole lot to it. This can now be viewed as the expectation paths governed by k of this e to the negative 1 over t p x t to tau, or to the terminal condition. Right, so immediately we have an estimator for this thing, the Monte Carlo estimator. The sum over paths, which will index I. That's kind of each path that we draw. Okay, and this thing, right, the interpretation is pretty clear, right? So before we had this HJB cone, all these states, and then the terminal condition, right? So instead of kind of summing over all possible transitions here, we just kind of draw a particular path from our probability distribution. We calculate the potential. This is our first path. Then generate paths according to the propagator k, and sum these exponentiated things together. Right, so I'll just keep things concrete, right? So we have our estimator of j can be written 1 over n. Of right, so pretty straightforward way to get z. Right, this thing should converge to z of x of t. Right, this initial point being our x of t, according to the law of large numbers. So the properties of that convergence might not be very good, and in fact we expect them to be pretty terrible in this using the simple algorithm. So this is really just the starting point. Although it works in simple cases, right? So there are cases where we're basically done. But in general, the statistical properties of this kind of sample are too poor to be used. And the reason is because you're taking the sum of exponentials. And a lot of times, usually, the thing you're interested in has the distribution of v has exponential tails. And so it's very possible that you're kind of dependent on extremely rare events, just the very best paths, which are very rare. And those paths will largely determine z, and everything else will contribute practically nothing. So there's kind of this dependence on extremely rare events, which is problematic. So the next step is to use what are so-called there's a ton of name for these things, but they're called particle filters. That name seems to be in vogue right now in the machine learning community. They're called transfer matrix methods. They're called, I don't know, some kinds of evolutionary algorithms. So they have a lot of different names, and the basic names. And the basic idea is that instead of evolving each path independently, you let these paths compete as they evolve. So you start with path 1, path 2, path 3. Put them all to the same time point. And say the object of your control is to keep things kind of in this region here. So if your control is successful, this path will be kind of good, and these paths will be kind of crappy, right? And you can tell they're crappy because, v of so if this is xt, this is x t prime, right? V of x t to t prime is kind of large, right? And same with this one. You've accumulated a lot of costs as you move along, whereas this one is kind of the winner so far. Right, so plotting these things, we see that basically that the potential is lowest for this one. So what you can do is you can treat this as a well, basically you're treating this expectation or this weight so you treat this as actually as part of the potential, or as part of the probability weight. So this is what's called importance sampling. Where you shift your distribution based on the expectation you're trying to take. And so what ends up happening is you say, okay, actually these paths, according to our new weight, are actually rare. So we're just going to say they just kill them off, and then this path is allowed to reproduce. So moving forward in time, this path, right, we allow these other two paths to kind of move forward. And that gives them kind of a chance to become the leader again, right? So, oops. Right, so you're not kind of wasting calculations, evolving these already crappy trajectories even further along in time. So it makes things much more efficient. So let me talk a little bit about importance sampling. So essentially, so the expectation of exponentials can be kind of really crappy. And one place where you can see this is in the chi-squared distribution. So if we have x is well, it already looks like a chi. If it's chi-squared distributed with d degrees of freedom, so that means it's equal to the sum of d normally distributed random variables squared. So this thing shows up a lot as kind of a standard distribution. If you have d dimensions and you rescale everything properly, then your total mean squared error will look chi-squared distributed. So this is an important distribution, and kind of one of the annoying things is if you take the expectation of x according to the chi-squared distribution of e to the beta x, this is the moment generating function, and it's pretty easy to show using a contour integral that this moment generating function has the form 1 minus 2 beta to the d over 2. Right, so there's a pole in this thing. There's a pole at, if we draw our complex plane, there's a pole right at 2, or right at 1/2. So, you can evaluate this thing over here when beta is small, but as soon as beta crosses this critical threshold, the expectation of this thing diverges to infinity. And that has kind of profound implications for Monte Carlo estimates, right? So if you're trying to take the expectation of something like e to the x, right, beta x, where I'll just mix up my notation a bit just because sometimes this is more fun to write. If you're trying to take this when beta is equal to Oops, it's an ugly beta. When beta is equal to 1, for instance, right? You might think that this could be estimated by the sum of xi, each xi drawn from a chi-squared, e to the xi. But actually, when you look at the, if you plot this estimator, so if you plot the partial sum here, this estimator, I'll write that like that, as a function of n, you'd see that the kind of fluctuations kind of become arbitrarily large. And the expectation kind of fluctuates around, but on average, it always increases with n. So even though these things are never infinite, right? It's just the expectation of a finite random variable that has no mass at infinity. The integral diverges, so you know that somehow this thing will also diverge. So kind of this paradoxical property of these things. And this is sort of representative of a lot of the problems that can happen if we don't kind of shift our measure around. So if obviously this thing has no proper Monte Carlo estimator, but if we're interested in e to the beta x, where beta is equal to, say, 0.4, so close to the pole but not at the pole, then we're still going to have roughly the same problem, right? This thing will increase, and something like, very, very slowly, it's going to approach some true expectation. But n might have to be absolutely enormous before you get there. So you might never actually reach the true value of this integral, which is kind of very annoying. So one thing you can do is sort of shift the tail of your distribution by beta x, and then draw from that distribution, and that thing will have much, much lower variance. So in the same way, we're kind of So the principle of importance sampling is that we have this integral is our expectation. So and this thing can be written just by multiplying and dividing by the density of a reference distribution. Right, this is equal to the expectation of f of x p x over qx, where before x was drawn from p, and now x is drawn from q. Right, so this is the idea that you shift your mass around, and if your new distribution is kind of, ideally you would get things in such a way that this is a constant, right? If you choose your weight function here in such a way that it's basically 1 over f, you can show that in certain cases if this is possible, this is the optimal thing to do, and then you end up with you basically need to know your answer beforehand. But just to close off this digression, our chi-squared distribution is something like x to the d over 2 minus 1 e to the negative x over 2, right? And so if you multiply by e to the, and if you're trying, and if we're trying to take this expectation, x is chi-squared, and beta is equal to, say, now it doesn't matter what it is, but it's close to 1/2, but not quite 1/2, then you can see that you can change distributions. Basically, if you multiply this and if you this is, this multiplied together is proportional to x d over 2 minus 1 e to the negative x times 1/2 minus beta. And you can see that this is kind of proportional to a gamma distribution now. So by shifting distributions and keeping track of your normalization constants, it's a gamma distribution with, your scale parameter is something like 1 over 1/2 minus beta, but then you still have d over 2 is your new, it depends on your parameterization, but that's kind of so you can combine these things together into a single gamma distribution, and then it's sort of completely well behaved. You have a very large scale parameter, but your degree of freedoms, your degrees of freedom are still quite large. So the variance is kind of well controlled, drawing from this new distribution. So so that's kind of the general idea. So now to return from our digression back to the path interval, right? We're interested in this sum over paths. This is our z. And if we view this as kind of shifting our distribution of paths around, we can draw from this distribution by this kind of iterative resampling, where you kind of propagate a bunch of different paths forward in time, and then you kill them off when they become too costly. And you branch them out, and then the paths that survive kind of tell you which things are really going to contribute to your expectation. So how do we do that? Well, at the time point t, let's say we're doing this resampling at a time point t prime, we have these v's, the potentials we've observed from t to t prime. And so we have this collection of particles that reach this time point t prime. So we have the set v1 all the way to vn at t plus t prime. And they're all functions of different x's from t to t prime. And then basically, since they're supposed to be drawn with weight, each path should be drawn e to the negative v I. So each path I should be drawn with this weight. So we can use this as kind of the path weight of I. So we can draw our new paths with there's a lot of different options, but we can draw them. In the simplest case, we could draw them using Bernoulli trials, or using a multinomial sampling scheme. So at the end, each path has the multiplicity of path I is given by just the binomial probability. Right, and so you sample them multinomially. This isn't actually the best way to do things, right? So all you require is that the expectation of mi be equal to n times wi. That's the only thing you need, is to make your new multiplicity, so how many paths you end up with at a particular weight, equal to this expected weight. And so one thing that's nice to do is to actually do what's called, I think it's called residual sampling or something like that. And that's where you say mi is equal to the floor function of this, so the lowest integer, plus some residual, right? So there's some residual Ri, where Ri is drawn from kind of whatever is left over. So you can imagine, let's Well, here, let's use, right, so our weights for different points. Right, most of them are very small. That's usually how it turns out. Right, so some of them, though, are well above, so let's say this is 1, 2, so this is WI, and this is 1, this is 2, etc. Right, so first you kind of keep track of kind of these integral parts. And then you sample from the parts that are kind of left. And so all these little tips that stick out, you can't, you have to draw randomly on those. But because you've taken care of the bulk using this deterministic method, you kind of drastically reduce the variance of your sampling. And that turns out to have really good properties because the variance of your, of how many times you choose each point, right, that tells you essentially how branchy your thing is, right? So if we go too far back in time, then all the different family trees converge and everything left here is just dead, except for the one ancestral branch. And the time to convergence in population genetics is called NE. It's the effective population size, or the neutral coalescence time. It's a much better name because it's a time, not a population size. And the amount of variance you have in how often an individual gives birth or dies determines this coalescence time. And if you want better sampling properties, you kind of want this branching to occur over longer periods of time, so that they're kind of competing for longer. And so you're gaining more information about, essentially about the normalizing factor that governs this distribution. So longer NE equals low sample variance, low drift. And so you can reduce the drift by doing this kind of more deterministic sampling. It reduces the variance of your multiplicities. So in the end, you resample your points according to this thing at these these resampling times. So you have these family trees that go until time t, or these independent paths basically, and then only 1 or 2 paths survive. So there's 5 total paths here. And so this one gets multiplicity of 3, this one gets multiplicity of 2. And then say, actually in this case only 1 survives. So at each resample time there's kind of this bottleneck where you figure out which path has been doing the best. And afterwards, so you have a v from 0 to t, v of x of t to t prime. Right, but afterwards you can set the path weights of all these things, all the v's to 0, all the path weights equal to 1, because you've kind of accounted for all the potential that the particle has seen in the resampling already. So you've already kind of used up that v. So so at this point here, you're just governed by, let's call this t, let's call it t2. So the path sampling here is governed by v of x from t1 to t2. So it's a much smaller span of time, and that means the variance of this thing is much smaller. And of course, since this is in the exponent, that means the variance of your estimator is going to be a lot smaller too. And so at the end, right, to calculate this c of x of t, I mean, the properties aren't good here. You're too far back in time. Your paths have completely coalesced, so you don't have great information. But you basically apply the HJB equation, but you only have to worry, the same kind of HJB recurrence, but you only have to worry about the paths that have survived. So you keep track of, essentially, so there's a final potential. Let's say this is our final potential. So there's a final potential in each path. Maybe this isn't the best example because it's kind of degenerate. But then to figure out how much this expectation, right, this expectation over of your thing, of your potential function. To figure this out, you just have to keep track of kind of how much mass. So the mass of each point is determined by this v at the end. Big, small v's have big mass and big v's have small mass. It's just e to the negative v final over t. And then you just keep track of, you don't have to worry about the mass ever again, because the mass is just, all the other potentials have been kept track of via resampling. So you just keep track of kind of how much mass flows back to a particular point. Right, so in this case, all of these guys flow back to this particular point, and nothing flows back to these. So, well, that tells you essentially that the cost on these is effectively infinitely higher. I mean, it's just a lot higher. The difference in cost is kind of beyond our resolution, and we only really care about this path, getting our state into this particular point so that it can survive. And if we miss this point, we're kind of out of luck. Now, that's a very small sample size. You can see that you'll need to actually estimate this density from your points, and that's kind of where the machine learning will come in. But this is the effectively all we really need to understand to get our z of x of t. So it's just kind of how much mass flows back along this family tree after resampling at each time point. But there's a catch, and that's that we've kind of lost track of the actual value of this. This is really just proportional to. We've lost track of the normalization factor when we do these resampling steps. So, or rather, we kind of add in this extra normalization factor. So that means, that means we only have access to things that are proportional to z at each time slice, essentially. And but that turns out to not really be a problem, right? Because in the end, we're interested in calculating things like the energy differences. So yeah, EU is given by the expectation of this thing times t. Plus the cost. Right, and if we don't have the normalization, right, that just adds a total constant to the energies, and when we calculate the control, that cancels out with the free energy. So the absolute value of the cost to go doesn't really matter. It's only differences across points in the same time slice that determines kind of which control we're interested in. And that's kind of sort of a universal theme, that it's really the differences in the cost to go that are the observable, and the absolute value of the cost to go is kind of not always easy or useful to compute.